Well, good afternoon. It's a little after, or right around 12:15, 12:16, something like that. It's Wednesday afternoon, the 22nd or 3rd of August 2017, and this is supposed to be Calculus 3, Math 227. The trouble is, I'm the only one in the room. So we'll continue from where we left off last time. We were talking about vectors in general, which is not very calculusly yet, but we will get to apply it to calculus. And I believe we were on page 726, chapter 12, vector geometry, section 12.1, vectors in the plane, and page 626, top of the page. And I'm pretty sure we covered the slide, and I was no, I'm on the wrong slide. Sorry, this slide is from the previous page. Nope. Yes, it is. Sorry, wrong slide. There's the slide we need to be on now. All right, sorry about that. All right. We were talking last time about vectors that were parallel to each other and translations of each other. All right. Now we're going to carry it a little bit further, talking about equivalent vectors. Okay. In the A figure here, of figure 3, A part of figure 3, all these vectors are equivalent to one another. They are all translates of vector v. Okay, they all have exactly the same magnitude and precisely the same direction, and they're pointed in the same direction. So therefore, these are equivalent vectors. However, under B, neither of those, the green nor the blue, are equivalent vectors. The green vector is parallel to vector v, but not the same magnitude, so they have exactly the same direction, but not the same magnitude. The blue vector appears to have exactly the same magnitude, but definitely not the same direction, so neither one of those are equivalent to v. Now, so we can move vectors anywhere we want to all around the plane, and there are sometimes when we want to do that. Later when we get into 3 space, we can move them all in 3 space as long as they maintain the same direction and same magnitude. However, the most commonly chosen translate to do is to move a vector v, like we see here, down to having its tail at the origin. All right, good. I'm glad to have someone to talk with and not have to talk to myself. Okay, so the day is the 22nd August, and Jasmine's here. So I got started. The lights. And the projector will be coming on soon. All right, it's slowly coming here. And what this is where we began today. These 4 vectors, the 3 not listed as V, are all equivalent to V. Why? Same magnitude and exactly precisely the same direction. How about B? There's a red vector is our listed vector V. What can you tell me about the green vector? It's what? It's parallel to V, but not the same magnitude, so that's not equivalent. How about the blue vector? Okay, it's not parallel, not going in the same direction as V. Appears maybe to be the same magnitude, I can't tell for sure, but it definitely is not the same direction. So, two vectors are equivalent if they're going in precisely the same direction with precisely the same magnitude. Now the C part of this figure illustrates the most common, but not the only time we translate a vector. There's vector V just hanging around there in the first quadrant. When we translate it down so its tail is at the origin, then we call this V sub 0. It's the unique vector based on the origin, whose tail is the origin. Origin is the origin, and it's equivalent to V. Okay? And it's the one and only. For any vector anywhere in the plane or in space, it's its V0 would be with its origin at the origin. Okay. The initial side, initial endpoint at the origin. Okay. That leads, sorta, but to a very important definition here. Okay? Components of a vector. The components of some vector PQ, now remember when we write a vector like this, always P is the initial point and Q is the terminal point. Always. When we write it like that, P is that. Where P is A1, B1, the initial point, and Q is A2, B2, which happens to be the terminal point of that vector V. Okay? Now, the components of that vector V, whose initial point is P, which is A1, B1, and terminal point is Q, which is A2, B2, the components of that would then be the difference of the components, final minus initial, always. Terminal minus initial, okay? Terminal minus, yeah, I guess that's fine. A2 minus A1 is the x component of that vector, and B2 minus B1 is the y component of that vector, A, B, okay? That pair of components is denoted as the vector AB, okay? That vector V, AB, would be the same if its initial point was at the origin or anywhere else in the plane. It will always have the same magnitude and always have the same direction. Now, something to note here. This book, like a lot of other fairly modern, I think, math books do, they designate vectors with angle brackets. Okay? Now I'm trying to remember, are you in linear algebra? You are, aren't you? Okay. Did you take pre-calculus here at Lawson? You did. The text we use for pre-calculus uses the same notation. It was written by Ron Larson, the same author as your linear algebra text. And yet in the linear algebra text, he doesn't use that notation. And it aggravates the fool out of me because there in the previous one, he used angle bracket notation for vectors and parentheses for points. See, that's a point, that's a point, that's a vector. Okay, parentheses indicate points, angle brackets indicate vectors. Makes great sense to do it that way. Okay? However, in his linear algebra book, he puts them in parentheses. Oh, why? You did it right the other way in your pre-calculus book. Why do you change here? Now, we just adopted his calculus text, but it's only being taught in Calculus 1, not 2 and 3 yet. That's what we're, because y'all bought this book, you still staying with it. I haven't checked to see if which notation he used in that. I don't know. Okay. So they sometimes call that initial point, they call it the base point, B, which is P00, the components of vector V. If you put the P to be 0, 0 here, then Q would be A2, B2, but that would also be A is A2 minus 0, so that would be your A is A2, and B would be B2. So that same designation here would be the terminal point of the vector. Same order, but you put angle brackets and that makes it the vector. So when the initial point is the origin, your terminal point and your components are identically the same. It's just that the terminal point has parentheses around it and the vector has the angle brackets around it. Okay, so components, coordinates, they even sound alike. You know, it can get confusing, just don't let it get to you. Okay. This is the figure that illustrates what I was just talking about. I should have gotten it up here to do it. This is initial point, or what did they call it? Base point. Base point P, A1, B1, terminal point Q, A2, B2. Then the components of this vector would be the x component would be A2 minus A1, which we're going to call A now, and the terminal point would be B2 minus B1, and that we'll call B now. If you translate that to the origin and make it its V0, then the terminal point here, now why they changed it and made it a P0, I would have called it Q0 maybe. I mean, I would have called that P0, 0, but they changed the lettering on it. It doesn't matter. The point is AB. The vector is still AB, but with angle brackets. Vectors V and V0 have components AB in angle brackets. So any two equivalent vectors will always have the same components. That's what it's getting at. All right. Now, I guess we haven't formally defined this yet, so let's do that now. For vector V, any old vector V, the magnitude, and that's what the double bars stand for, magnitude. What do they sort of look like? Double absolute value bars. And that's the good correlation to keep in mind. Because guess what? The magnitude of a vector, just like the absolute value of a number, is always going to be positive. You cannot have a magnitude of a vector being negative. Okay? Now, the magnitude of vector V would be the magnitude of the vector PQ, and that magnitude is always going to be the principal square root, meaning positive square root, that's why it's always positive, of the first component squared plus the second component squared. Now, if this was a three-dimensional vector, it would be the square root of a squared plus b squared plus c squared. If it was an n-dimensional vector, which we can't draw, but you can conceive of it, that would be the square root of a1 squared plus a2 squared plus a3 squared up to a n squared. Okay, so that's the definition of the magnitude of a vector. The square root of the sum of the squares of their components. Now, here's another thing, and this is kind of a pain in the neck to me, but you have to have it, otherwise it's hard to deal with. I'll get to that later. The zero vector. Zero vector is sort of problematic for two reasons. It has no magnitude and it has no direction, okay? And that's what a vector has to have, a magnitude and a direction. Well, a zero vector, components are 0, 0, okay? So its magnitude is 0 and its direction is completely undefined. Because where do you point a vector that has no, that's a single point? There is no direction for it. So, but you have to have it in there or else you can't do other things. So the zero vectors whose head and tail coincide at a single point, wherever it happens to be, the vector, and by the way, when they refer to the zero vector, my pen activated again. When they refer to the zero vector, they write it bold. I can't write bold, so I put the arrow over it. Okay? And this vector would be the vector whose x component is 0 and whose y component is 0. Okay? So it has components, but they're always 0, 0. So it has 0 magnitude, meaning no magnitude, and absolutely no direction. It could be pointing anywhere, but you can't tell because it's just a single point. Okay. Now, they do a little blurb on the side. You don't have your book yet, but it says, in this text, the angle brackets are used to distinguish between a vector, V, AB, and the point, P, AB, in parentheses. Some texts denote both V and P as AB, as in linear algebra. Okay. When referring to vectors, we assume the terms length and magnitudes are interchangeable. So if it says length of a vector, that's the same as magnitude. The term norm of a vector is also used for length or magnitude. Not so much in this text, but in linear algebra, we'll see norm is used a bit more. Norm, yeah. So it's the same as magnitude or length. All right, now if my memory's right, we're just sort of PowerPointing our way through here and not necessarily doing any exercises. So I won't do exercise 1, but I think they have a, well, they don't have a graph of it. Okay. Here's a little statement here. I don't see it in our text, but it's worth noting. Sorry, I'm having a hard time breathing. Okay. We assume that all vectors are based on origin unless they're otherwise stated. So when it gives you a vector, picture that at the origin. Assume it's at the origin. If for some reason the way you're working the problem it can't be there, it's okay, you know. But if it's not some reason it can't be, then just assume they are at the origin. Excuse me. All right, here is the figure for example 1. And again, we're not going to do it, but let's just sort of talk through it a little bit. Okay. It gives us two vectors based on their points. Their base point P's and their terminal points Q's. P1, Q1, and P2, Q2. Are these equivalent vectors? What think you? In other words, V1 and V2, are they equivalent? You don't think so? Or you do? I couldn't hear. No. You're right. Okay? Looking at it, though, isn't the best way to do that. The best way is calculate their components. What's the components of V1? Okay. Okay. My hearing's bad, so I'm not quite sure what you said. It sounded like most of it was right, but you calculate what?
You calculate A
and B. Oh, A and B, I know from the previous thing. Okay. What are they in this one?
So A is 6 minus 3, which is
right. 3.
And then B is 5 minus 7.
right?
Which is -2.
-2. So this vector V1 would be, I can't write on there, so just imagine it's there, is 3, -2. Okay, do the same thing for V2.
So V2 is 3 and -3.
-3. So the x components are the same, but the y components aren't. Just so looking at those, if they don't have exactly the same components, they're not equivalent vectors. So looking at them, parallax, other things, you might guess wrong, but calculating the components gives it to you every time. Okay, good. Now, all right. I know what they're getting at, but it seems like a weird way to run around to get it. Here's vector V, which is PQ. They did the calculation for you. 3 minus 1 is 2. 1 minus 4 is -3. So there's a vector whose component is 2, -3. Here's a vector, V0, also with components 2, -3. It's at the origin, so basically this terminal point is 2, -3. Sure enough, that's the same. Those are equivalent vectors, but they have different base points. Vectors V1, V and V0 have the same component but different base points. So they're, in a sense, not the same vectors, but they're equivalent vectors, or we actually will start calling them equal vectors. Somehow it seems like equivalent is a little more Weasley of a word that includes everything. All right, now let's move into vector algebra. What if we're trying to manipulate vectors? Okay. Goodness, my eye is hurting. My right eye, I don't know why. It just has started. I think I got it all on there. Yeah, I do. Okay. Now, when you're adding two vectors, V and W, this is not the easy way to do it, but it certainly works. Okay? V plus W, if you start with V and then translate W so that its base point of W is at the terminal point of V, and that gives you, puts it up here, then draw the vector from the base point of V to the terminal point of W. That gives you what you call the sum vector. Okay? So what they did is not just translate it, but they gave it a new color and a new name. They said blue vector W, translated up here becomes green vector W prime. Okay? So the first thing to do is that. Like I said, back when we were talking about this, they said most of the time we'll assume that the base point is at the origin. Not when we're doing basic, a vector addition. Here it could have been at the origin here, but it makes more sense to do the addition by putting the base point of W on the terminal point of V. So, and that's what we did and called it W prime. You could have left it W because they have the same components, and then draw the line connecting the base point of V to the terminal point of W. And that's your sum vector. And by the way, you add two vectors, you get a vector. Okay? That's what we've just done. Now that form of addition using graphical means to add vectors, that's sometimes called the parallelogram law. In other words, draw your V and W and then draw a line parallel to V and a parallel to W, and then the diagonal from the common base point to the opposite point will be of that parallelogram, your sum. Okay? Now, that actually leads to another concept indirectly, but it really leads there. When you do v plus w like this, you get this vector. But what if you had chosen to do w plus v? You get the same sum. So what this leads us to conclude, and we'll get to it later, but the pictures say it all, is that the vector addition, which is what we're doing here, is commutative. It doesn't matter the order in which you add. Okay? So vector addition, just like scalar addition. 3 plus 7 is the same as 7 plus 3. Okay? They are the same. You can commute the two. And same with vectors. That won't always be the case, however. Okay. Now, what if you had a whole passel or a half a passel of vectors? Okay? Goodness gracious, my eye hurts. I don't know why. All right, here we have 4 vectors. V1 down in the 4th quadrant, V2 up in the 1st quadrant, V3 over here in the 2nd quadrant, and V4 down in the 3rd quadrant. What if you wanted to add those 4 vectors together? Okay? Now, we've already established the order doesn't matter in which you add. Neither do the associations. Okay? So, if we started with vector 1 and added vector 2 to it, that would bring us over here. And then add vector 3 to that, that would give us up here somewhere. And then vector 4 to that would bring us down here somewhere. Okay? So we should wind up with a vector over here in the 2nd quadrant. And sure enough, we do. So why now they started putting primes on, I'm not sure. Because this V1 is the same as that V1 prime. So why change the name? But this V2 is equivalent to this V2 prime. So maybe just for the equivalence. This V3 is equivalent to that V3 prime, and then this V4 is equivalent to that V4 prime. Okay? So your resultant, sum, whatever you want to call it, vector, will be from the terminal point of the first one to the, from the base point of the first one to the terminal point of the last one. There's your vector V. Now, what if you had started with V2 and add to it V3 and add to that V4 and add to that V1, you sure enough get the same vector. And any way you want to combine those. Well, that's a sort of subtle way, maybe not too subtle, of saying not only is vector addition commutative, it's also associative. Doesn't matter what order or associations, which ones you add first and then add to the second, and whatever. So vector addition is both commutative and associative. All right. Now, whereas we've been, referring to vectors which have magnitude and direction, if something only has magnitude, well, we used to just call that a number, right? In terms of vectors, we call it a scalar, okay? Just a number, a pure number, with no direction associated with it is called a scalar. And in one sense, it's what you use to scale up or down another vector. Say if this was your initial vector, and you multiply it by 2, it's going to keep the same direction but have twice the magnitude. Or if you take it and multiply it by 1/2, it will be half the magnitude but the same direction. Okay? And if you multiply it, or what would be the best term for it? My eye hurts. I can't think of a precise word for it. But if you adjust it, you might say, by just flipping its direction. Basically, that's multiplied by -1. So it can scale up, making it longer. It can scale back, making it shorter, or it can reverse its direction. Okay, those are the three things that a scalar, meaning just a number, any real number, can do with a vector. Okay, now it looks like to me, here we go. Go back and talk about this slide. I was concerned because it seemed to be a little out of order. Yeah, it is. So let me go and hit it first, and we'll come back in a second. Gracious. I don't think I'm about to have a migraine, but the light is just really doing crazy things to my eyes. And that sometimes happens with migraine. I've only had like 2 or 3 in my life, and this doesn't feel like it's anywhere close to that, but I hope it's not. All right, well, we really need to do this slide first, okay? I was going to go, but that's moved into vector subtraction. Let's do this one first. It shows up first in the book. This is called, when you're dealing with, they sort of skipped over some stuff, okay? I sort of said it, but let's go back and actually deal with it. A scalar is just a number, okay? And if you multiply a scalar by a vector, and I already said this one, if the scalar, I didn't quite say it this precisely, but if the scalar is greater than 1, then it's going to increase the length of that vector, okay? If the scalar is between 0 and 1, then it's going to reduce the length of the vector. So you scale it up or you're scaling down, okay? Now, and then if it's x equal to 1, you have the same vector. 1 times a vector is just a vector. Okay. Now, what about the magnitude of a vector that you have multiplied by some scalar? And here the scalar they're representing with the number lambda. Okay, why they choose lambda, I don't know. Quite often they use the letter C. Here they use lambda. So if you multiply a vector v times lambda, now remember that lambda, there's no limit on it. It could be a decimal number, a fractional number, a whole number. It could be anything. It can even be a negative number. Okay? If it were negative, that would change the direction of that vector v. Okay. So, if you're talking about the magnitude of a scaled vector, a vector you multiply by a constant, a scalar, the magnitude of that will be the absolute value. Remember how you said things are similar, or they look similar? Well, they are. The absolute value of the scalar times the magnitude of the vector. That's what the magnitude of the scale vector will be. So in other words, it's still always positive. Because you see, lambda could be a negative number. And if you pulled it out, then it would make a negative times the magnitude of the vector. We can't have that, so it has to be the absolute value of lambda times that. Now, all right. If that lambda is positive, though, the scaled vector lambda v will be in the same direction as the vector v. If lambda is a number greater than 1, it'll be a longer vector. If the lambda is, remember, always positive, in this case, between 0 and 1, it's going to scale it down, make it shorter. Okay. Now we're kind of ready for this one. Really not quite. There's let me zoom in first. It did this to me earlier. In my last class, suddenly the cursor disappears. Let's see if I can do anything to get it back. Every now and then it goes into square, but the rectangle. Okay. Now it seems to be working better. Okay. I hate to do this. I've got to go get something. Let me put a pause on here. All right. Now, this figure here moves into vector subtraction. And, yeah, it's why I wanted to do that other part first, is, okay, to start with, what if you are given vector v and you want to subtract from that vector w? Well, if you remember the rules for signed numbers when you're subtracting, what do? When you're subtracting signed numbers, like -7 minus a -3. Yes, okay? Because what you do is change the minus to a plus and change the sign of the second one. That's what you do here too, is this would be equivalent to v plus the opposite of w, okay? The negative of w. And that's what they've drawn here. Here's v, and there is the negative, there's w, so the negative of w would be exactly the same length, but in the opposite direction. So there's minus w, and if you add v to minus w, translate the minus w up here, okay? Then by the parallelogram rule, there's your v minus w. Okay? Now, they say more simply, v minus w is the translate of the vector pointing from the tip of w to the tip of v. Okay, that might be a little simpler, but I have to then remember which tip is which. First, I find it easier to do this. To me, just think of v plus a negative w, that's it, okay? This also works. The drawing is simpler, but you have to remember it's from the tip of w to the tip of v, and not vice versa, okay? So, to me, there's more opportunity for error that way than there is this way. This way, to me, is more straightforward. Okay. Now, we've already done that slide. Not that we had to, but I thought to think of multiplying first by a negative number, which they hadn't shown you, but we just did. Now, here, this figure combines several things together. I'm trying to find this figure in our text, and I do not see it. Oh, there it is. There it is. Okay. I haven't looked far enough. I was looking down, not up. Okay. Again, my eyes are focused. Here's a vector v, the red vector v. Okay? If you multiply that by a scalar greater than 1, as in 2, then that would give you double the magnitude, but have exactly the same direction. Okay? The vectors v and 2v are based at p, but 2v is twice as long. Okay? Vector v and minus v are both based at p, but they're in exactly the opposite direction. Exactly the opposite direction. V and minus v have the same length, and they do have the same length. Remember, magnitude is always, and length is always a positive number, so the direction it points doesn't matter. The magnitude and the length are exactly the same. Okay. Because it's the square root, principal square root of the sum of two squares. Squares are always positive. The sum of two squares is always positive, and the principal square root is always positive. Okay. Now, let's go to this slide first, and then we'll come back to that definition, or I'm trying to keep it the same order of the book, and sometimes this is hard with this book or this slide set. I don't know who's the fault here. Okay, so this is illustrating certain operations. We already did this one. Vector v plus vector w is equal to the sum of those two. Okay, that's the sum. Okay, now we did it pictorially. Let's take a moment and look at it by components. This is the way to go. Don't do vector addition by parallelogram method or something else. Do it by components. Okay? Here's vector v, a in the x direction, b in the y direction. Components a, b. Here's vector w, c units in the x direction, d units in the y direction. Okay? Well, if you take this and translate it here, then your c becomes this, and your d becomes that. Okay, this is translation. Okay, what is your resultant vector? A plus c in the x direction, b plus d in the y direction. Hey, that's how we add vectors. Add component to component. A plus c, comma, b plus d. And it doesn't matter the order. Okay? So by all means, vector addition, so much easier if you just use the components. Straightforward and there. Okay. And then for some reason, B is sort of like we've never seen this before. We just used it here. Here's vector A, and there's vector AB, A in the x direction, B in the y direction. Okay. Well, what if we were going to multiply this by some constant? Now, this isn't exactly 2 or anything else, just any constant lambda. This is what that earlier slide was showing. Then, you're multiplying the x component by lambda and the y component by lambda. If that lambda was 1, you'd have exactly this. If it was 1/2, it would be here. 2, it would be there. Any lambda anywhere between 0 and infinity, you keep the same direction and either shrink the vector if it's less than 1 and lengthen the vector if the lambda is greater than 1. Okay, makes sense? Okay. Nothing too new. Not much calculus here, is there? Okay. Let's go back to these operations. Don't worry, that's coming. I don't remember if I asked you before. Have you taken physics yet, or are you taking it now?
I'm taking it.
Take it? This semester. If you haven't hit them yet, you're going to hit them soon, so you'll be a leg up on Okay, vector operations using components, and this is what we were just showing. If vector V is components A, B, angle brackets, and vector W is angle brackets, and neither is Victor. By the way, I forgot to circle your names. I'm circling them now. Okay. I don't know if we're going to see Sylvester McCrew or not. All right. If those are components for W, C, D, then when you're adding two vectors, don't mess around with drawing parallelograms and stuff. Just add the components. First component of V to the first component of C. That gives you the first component of the sum vector, A plus C. Add the second component of V to the second component of W, and that gives you second component of the sum vector, B plus D. And even easier. So don't worry about adding minus W to V or adding, doing tip to tip or anything else like that. Forget all that. I mean, really, the easiest thing to do is when you're subtracting two vectors, subtract the first component of the first vector, subtract from that the first component of the second vector, A minus C, comma, second component of the first vector minus second component of the second vector, B minus D. There it is, a literal piece of cake, okay? So easy to do. And if you're multiplying a vector by component, by a scalar quantity, you just multiply each of the components by that scalar quantity. So lambda times vector V, which would be AB, V lambda A, the vector lambda A, comma, lambda B. And then here's that last one, the really weird one. Adding the zero vector to any vector doesn't change the vector at all. Vector V plus zero vector is the same as the zero vector plus vector V, and that would be A plus zero would be A, B plus zero would be B. 0 plus A is A, and 0 plus B is B. So you get the vector V without any change whatsoever, because the zero vector has components 0, 0. Okay? So you're not changing anything at all. Okay, we're on page 628, chapter 12, vector geometry, section 12.1, vectors in the plane. Okay. Oh, this is the figure we already did. Okay. Now this is the figure for example 3. Okay? Pretty simple. Well, let me blow it up. All right. What they asked us to do was add two vectors. Vector V is 1, 4. Vector W is 2, 3. The sum of those two vectors is 1 plus 3 is 4. 4 plus 2 is 6. 4, 6 is your sum vector. They drew the parallelogram in there. Fine. It fits. It does perfectly. The easiest thing to do is add components. Component by component. Okay? And here's theorem 1. Earlier I began having sort of strobing kind of light in my eyes, and it's like it's hurting, and I had to take a break and go down to my office and drink some very cold water and put paper towel, wet paper towel, cool wet paper towel on my eyes, and that made them feel better. And now it's almost feeling like it's coming back again. But let's see if we can do it. The basic properties of vector algebra. For all vectors, U, V, and W, and for any scalar lambda, okay? And this I've already suggested to you. The adding of any two vectors is commutative. Vector V plus vector W is the same as vector W plus vector V, because all you're doing is adding their components, component by component, and because components are just scalar numbers, and numbers are commutative when you add them, then vectors are too. Associative law, it doesn't matter how you organize it. U plus the sum of V plus W is the same as the sum of u plus v added to w. It doesn't matter. So vector addition is commutative, vector addition is associative. Now be careful on this one. It's the distributive law for scalars over vectors. Now, I say it that way, they just say for scalars. Okay? If you have two vectors you're adding together, but you're multiplying the sum times a scalar, that's the same as multiplying the scalar times the first vector plus the scalar, same scalar times the second vector. So you basically are distributing the scalar inside the vector addition. Okay? Now the reason I said be careful, okay, you can't do this if there's a vector on the outside and the two vectors on the inside, because we haven't defined vector multiplication yet at all. So don't try it. There's actually two ways of multiplying vectors, and you have to be very careful when you're doing this. All right. Now, there is one other. If you had a vector on the outside and the scalars, sum of two scalars on the inside, well, that would be just what you would expect. That would be, let's say you have v out here and lambda plus mu in here. So v times lambda plus mu would be lambda v plus mu v. Yeah, mu v. And so that would work that way too. But they didn't show you that, so don't worry about it. Okay. Now, this is a figure that's trying to illustrate a couple of things at once, I believe. Okay, first, concept of linear combination of vectors v and w. Okay? A linear combination of vectors v and w would be any multiple of v plus any multiple of w. Okay? Now, here is sort of the picture of that. Here's the original vector v, the blue one, and here's the original vector w, beginning at the origin and going up to the tip of the blue there. Even though you can't see the blue here, it's under there. Okay. Now, if you're talking about the linear combination of these two vectors, it would be any multiple of v, okay, which could be a short multiple, a long multiple, or a negative multiple, short or long, okay? They chose to show the r being a negative number between 0 and negative 1. Now, it shortened the length, but went in the opposite direction. Plus any multiple of w. And again, that could be a small, something less than 1, greater than 1, or negative, okay? They showed something positive but less than 1. So this would be your SW here. You scale that one down, you reverse the direction and scale it down for V. Well, what would be the U vector, which would be that linear combination of U and V, okay, RV plus SW, that would be this vector here, okay? And actually doing it by components would make more sense, but they didn't give you the components here. Now, that is a linear, this is a linear combination of those two vectors. Yes, it is. Now, this illustration, which linear combination does allow this, allows R to be any number in the world from positive infinity to negative infinity, same with S. Okay? Now, if, however, we limit the R and S, say to be only are only positive numbers, so you don't have any negative numbers back in this direction, but it can be small negatives, large negatives, whatever. But we also limit S to be less than 1, okay? Not necessarily, well, actually they allow it to be negative the way they phrased it here, but up here they said S has to be between 0 and 1. So this is not the same as that. I think this is what they meant. They should have. Never. Oh, sorry. I thought this comma separated these two things. It doesn't. This is saying 0 is less than or equal to R and S, and R and S are both less than or equal to 1. Sorry, that's what they're meaning here. Now, if you do this, and this is your V, there's your W, then if R and S were both 0, you're at the 0 vector. It's right there, 0, 0, okay? If R and S were both 1, you would be R plus W, there would be the limit there. And if R and S is anything positive between 0 and 1, then it covers this khaki area in here, okay? And anything in here. And this is what we mean by this parallelogram spans V and W when R and S are between 0 and 1. If you let R and S be between -1 and 0, this one would be down here then, okay? If you allow R to be up to twice, up to 2, S to be 2, then you would have twice as big a thing. So that's what we mean by spanning. All the possible vectors you can get out of the linear combination of those two vectors with whatever limitations you want to put on the scales. Okay. We're saying that now. I don't think we'll use that anywhere else in this course. Linear algebra, you'll hit these terms again. Linear combinations and spanning. You probably will hit linear combinations of things later. I can't recall that we use spanning anywhere else. But anyway, that's what it means. This is a visual of it. When you get in the linear algebra, they just talk about it abstractly. This is a good visual for that. Okay. Now here's a picture, a figure, that goes along with example 4. We're not going to do 4, but just so you'll have some context to put it in. Here's a vector U, which is 4, 4. That's gracious. Here's a vector U, which is 4, 4. Okay? It says, express that vector U, 4, 4, as a linear combination of V, 6, 2, and W, 2, 4. So there's V, 6, 2, W, 2, 4. Okay? Basically, what you would do is exactly this. RV plus SW is equal to 4, 4. That's what you do. That gives you two equations, two unknown. 6R plus 2S is equal to 4, and 2R plus 4S is equal to 4. Two equations, two unknown. Solve them, and you'll come up with those two equations. Okay? I'm not going to stop and take time to do it, but you can probably get that done pretty simply. Okay? Any questions on that? Okay. All right, now I've got to find where this is. Oh, okay. Okay. The conceptual insight is basically what we just did. Okay. Remember we said vectors, how do we define the length of a vector? You remember that? What's another word for length of a vector? Magnitude of a vector. So what's the formula or equation for the length or magnitude of a vector? Say the vector v is AB. What would be the length or the magnitude of that vector v? The square root of a squared plus b squared. Excellent. Perfect. Okay? Now, what if I told you this vector v has a length of 1? Okay? Then the square root of a squared plus b squared would have to equal 1, right? Now, any vector you have that meets that criterion, that the magnitude of that vector is exactly 1, or that square root of a squared plus b squared is exactly 1, then, and by the way, if the square root of a squared plus b squared is equal to 1, that means a squared plus b squared is equal to 1, because the square root of 1 is 1. So you can lose the square root on it. If that's the case, then we call that a unit vector. No matter which direction it's pointing, if its magnitude is 1, wherever it's pointing, then it's called a unit vector. Now, I think this is fairly common in some other text as well. But I really don't like the E to represent unit vectors. It's perfectly okay. There's no problem with it. It just makes sense to me. Why didn't they call it U? Okay? Because I think of E as exponential. I think of E as lots of other things. I don't always think of it as a unit vector. Whereas I know they like to use U all the time. But frankly, to me, the easiest way to do this is to write U with a hat over it. And the hat to me indicates unit vector. Or anything. You can call it F or P or Q or E or anything. But put a hat over it, and that's what indicates to me it's a unit vector. They use the symbol E. Okay? And at one time it seemed like I figured out maybe why they did that, but I don't remember what my reasoning was on it. But I don't know. Now, so a unit vector has magnitude 1. It can be in any direction whatsoever as long as it has magnitude 1. Well, what if we want a unit vector in the direction of the vector v? That's the vector we were given. Happen to have a vector v here. How do we determine the unit vector in that direction? Okay? Well, the magnitude of v is this thing, the square root of a squared plus b squared. Okay? And if that's greater than 1, that's not a unit vector. If it's less than 1, it's not a unit vector. If it happens to be exactly 1, it is. Well, if you divide the vector v by its magnitude, okay, this vector v could be expressed as the magnitude times the unit vector in the direction of v, and okay, I think I just said this, vector v is the magnitude of v times the unit vector, because the unit vector has magnitude 1 in the direction of v. So if you really started with that, vector v is the magnitude of v times the unit vector in the same direction as v, then divide both sides plus magnitude of v. And this is how we define a unit vector in the direction of v. Okay? we will be using that a little bit, so stand by and get used to it. Why they didn't show this on the slide, I think I'll write it here. They actually did it first. Here is a unit vector, E. And, okay, remember I can't write bold. The book does, okay? And usually when you talk about any old vector, you put an arrow over it. I like to use the hat on top, caret they call it sometimes on top, to indicate that's a unit vector. So when you see me write that, you know it's a unit vector. So the unit vector E, one of these is goodness gracious. Eyes are doing it again. I don't know, it feels like closing them makes them worse, so here I am closing them. I'm trying to get it to settle down. Okay. Here is a guaranteed unit vector. Sine theta, cosine theta. Now, the thing is, they write it the other way, and I know why. So let's go on and write it the other way. Cosine theta, sine theta. Both of them are unit vectors, by the way. Okay. Why do I say it's guaranteed to be a unit vector? What was the definition of the magnitude of a vector? Yeah, the length. And what is that? A square root of a squared plus b squared. So let's do it. Let's do what you just said. So the magnitude of this vector, E, which I'm claiming is a unit vector, but it doesn't necessarily have to be, would be the square root of cosine squared theta plus sine squared theta. And guess what, team? For any angle theta, what's sine squared plus cosine squared? Say again? 1. And the square root of 1 is 1. So sure enough, this has to be a unit vector. Okay? Always. Okay? Now, stand this. Started again. So there's basically your good old unit circle. And everywhere on that unit circle, when cosine theta is equal to, as small as it is, sine theta, sorry. Yeah. Okay. For any angle theta, cosine theta, sine theta is a unit vector because the square root of cosine squared theta plus sine squared theta is 1. Okay. I guess that's really all you need to say about that, because as theta is 0, cosine 0 is 1, sine 0 is 0. So you're at 1, 0. Okay? pi halves, this would be 0, 1. Pi would be negative 1, 0. 3 halves pi would be 0, negative 1. And then every angle in between, square root of 2 over 2, 1 half square root of 3 over 2. You just go around the circle and you always have radius 1 because sine squared plus cosine. Okay. Now, somewhat of a weird looking thing to do to that nice unit vector. I don't know, it's something almost from looking at that to looking at this is doing crazy things to my eyes. I don't know what. You would think looking at this would be brighter and that would hurt more. Actually looking at that is. And I don't know if I'm picking up the strobe that I can't distinguish, and that's what's doing it. I don't know what it is. Okay. Now, okay. This is sort of doing the same thing we just done. Here is vector V going out there to AB. Here they chose A to be greater than 1, B to be greater than 1. It could have been AB in here, or here, or here, or there. You know, anywhere. AB could be anywhere in that mix. Okay? Well, let's just use this AB. There's your vector V. Now, the unit vector in the direction of V would be of all the unit vectors in the world around that unit circle, the one that's in that same direction, pointed in the same way, that's the unit vector in the direction of V. It has to be a unit vector, and it's in that same direction. Now, I'm not sure they're going to do this, but let's do it because it's fun. Okay? This represents some angle theta. Can you tell me anything about that angle theta? Anything at all about that angle theta? Okay. Let me remind you, this vector V has x component A, B component B, y component B. Can you tell me anything about that angle theta? What is that angle theta? Take it? Yeah, it would be heading that way. Second? Okay. Looks like it could. I think it's a little past 45. I'm not saying exactly the number of the degree, but can you define that theta for me? Okay, let me do this. This length here is B, right? This length here is A, right? And how is this angle theta related to that side and that side? Not parallel to this or to this. But how is this angle related to this side and that side? Neat trig functions. Second? Okay, which side would you say is an adjacent side to this angle theta? A. A is the adjacent side, and what? Okay, hypotenuse is here. I don't know B's about it. But I do know that B is the opposite side. Isn't it? Opposite this is that length there, which is the same as B. Okay, so therefore this angle theta is, okay, and how is the opposite side and adjacent side related to an angle? What trig function? Tangent is which?
which means?
The tangent is what? How is it related to the opposite side and the adjacent side? Do you remember the little acrostic? Some old hen? Have you ever heard this one? What's that? Yeah, Sakatoa. Is that what you said? Yeah, it's like that. If that's how you remember, it's perfectly fine to use that. But I had a student tell me this one, and it found it pretty interesting. I'm going to have to shrink it to write it down. Some old hen caught another hen taking oats away. The sine of theta is equal opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse, and tangent of theta is equal to opposite over adjacent. That's the one. So the tangent of this angle theta is equal to the opposite b over the adjacent a. Okay? Well, guess what? That means theta would be the inverse tangent of b over a. That's not what they were getting at, but since we had the picture here and it looked pretty obvious in it, I was hoping it would be anyway, that's how you can tell the angle theta, okay, for that particular vector v. Okay. Now, with that done, all right, we know the vector v, as we already said, was a, b, right? That was the components given to us to begin with. Well, that vector v is also the magnitude of v times the unit vector in the direction of v, okay? Now, by the way, that's one way to express any vector is to its magnitude times its unit vector. Because the unit vector's got to be in the same direction, but the magnitude of unit vector is 1, so multiplying by the magnitude of v gives you exactly what, well, within a plus or minus sign, let me put it that way, of the unit vector v. I hadn't thought of this. Do have a little bit of a problem here. No. That's fine. No, you don't have to worry about plus or minus at all, because this is in the direction of v. That's how that is defined. The unit vector in the direction of v. So your direction is fixed in the right direction, and then just multiply it by its magnitude, and you got the vector v. Okay? Well, let's see. Remember we said that vector, any unit vector can be written as cosine theta sine theta. Once you know what the a and b is, the theta is the inverse tangent of b over a. So once you know that, then that theta can be plugged in here. Okay? Any vector e can be written as cosine theta sine theta for the right theta, and we know that theta has to be the inverse tangent of b over a. They didn't mention that part, but it is true. Or if they did mention it, they left it off the slide set. Okay. I think this is an example, but let's take a look at it and see. Oh, okay. This is jumping. No. In rectangular coordinates, okay, we generally will talk about the unit vector in the x direction is always being the unit vector I, and the unit vector in the y direction will be referred to as j. All right. Now, when I write these, because I don't write bold, my little I has a hat over it and little j has a hat over it. That's how I write these, because those are unit vectors. But these are very specific unit vectors. These are the ones that are along the x-axis and the y-axis. Later, when we go to 3 dimensions, unit vector in the z-axis will be k, ijk. Okay? So any vector v can be written as a, the component of, in the x direction, ai plus bj. So here is another way of writing a vector in component notation, but this is in unit vector notation. Now, sort of shows how old I am. I don't ever remember our using just component notation, like angle bracket. Well, I don't ever remember using angle bracket. A comma B angle bracket. That's sort of a new notation. When we wrote it in component notation, this is how we wrote it. AI plus BJ. That would be your vector V. It's a lot neater to do angle bracket A comma B. Okay? But I don't recall that we had it that way back then. If A is greater than 1, it's like this. If A was less than 1, it would be right here. B less than 1, it would be over here. Okay? If A were negative, which A can be negative, okay, it would be over here, so that one would be pointing this way. If B were also negative, it would be in the 3rd quadrant. But if A were positive and B negative, it would be in the 4th quadrant. Gracious, I'm almost dizzy now. If you hadn't caught on or noticed this yet, here's another way to write those ij vectors, unit vectors. I is always in the x direction with no component in the y direction, so it's going to be a 1, 0. It's got to be a unit vector. So since there's no y component, the x component has to be 1. And similarly, j has no x component, the y component has to be 1. So these are the other ways you can express ij. Always easier to just say ij, but these are the vectors that represent ij. Okay? Now, pretty sure this is just a example 5, so I won't tell this down and go over it with you, but I think this is example 5. No, this is conceptual insight, I think. I can't tell. Okay. Now, these are usually fun type problems. When it sets up a when you're trying to solve a physics problem like this one, and you may not have gotten there yet this term, but you'll get there, believe me. You have 2 fixed points here. Cable 1, cable 2 happen not to be the same lengths, okay? And you have a 100 kilogram mass hanging at point P, okay? That's your physics problem. Now, if it's hanging there at rest, still, okay, that means the net force on that is 0, because it's not moving, right? What are the forces acting on this? Well, gravity is certainly pulling that mass downward. But the cables, cable 1 is pulling it this way, cable 2 is pulling it that way. Okay? Now, what we do typically there is break this problem into components. Okay? Now, you have to do a little bit of figuring here. I wasn't going to spend too much time on this. I'll just try to, okay, if you picture this as the, draw a parallel line to the upper one here, okay? Now, the x component of the book is calling these forces. Quite often in physics we call them tensions, which are forces, by the way. Force 1 and force 2 we usually call T1 and T2. So if this is T1 here, it's pulling in this direction. This is T2 in that direction. They're calling it F2. Now, notice that the length of this and the length of that have very little to do with the magnitudes of the forces. So don't feel like they have to be the same. Just label it F1 or T1 here and F2 or T2 there. Okay, and then what you do is, if you drew a line parallel here, you know that the, goodness, I can't think what they call those angles. Alternate interior angles between that parallel line to this one and the interior angles here, the interior angles there. Okay? So if you drew this, this will be 55 degrees here, this is 30 degrees there. Well, the x component of this force here is F1 times the cosine of 55 degrees. That would be the component in the x direction. The component in the y direction would be F2 times the cosine, times the sine of 55 degrees. The horizontal component here would be F2 times the cosine of 30 degrees, which you know would be square root of 3 over 2. And the y component would be F2 times the sine of 30 degrees, which would be 1/2. Okay, so now we've broken those into components. The components here, F1 times the cosine of 55 degrees, and F2 times the cosine of 30 degrees, which is square root of 3 over 2, those have to be equal and opposite to each other. Okay? In other words, well, let's just say they're equal to each other. Okay? They've got to be, because the sum of those two is 0. One's a negative variable, one's a positive. Because it's at rest. And the sum of the sines, F1 times the sine of 55 degrees, plus F2 times the sine of 30 degrees, which is 1/2, those two added together have to equal to the force downward, which is 100 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. And that's where they get this number here. Okay. So basically, that's what we do to set that up. Now, what they do a little differently from what I just said, I was taking this and saying this component here has to equal that component there, but how they do it is a little more precisely. Do your 30 degrees here, and this angle here would be 180 minus 55, which is 125. And you use that angle, and then you have the cosine of this one plus the cosine of that one is going to be, this has a negative cosine, that has a positive cosine. So that has to add up to 0. All right. You can read the rest of that problem. I probably did more than we should have there. All right. They gave here the cosine and the sines of 125 and 30 degrees, like I said. 30 degrees is square root of 3 over 2, which is what, 866 approximately. and the sine of 30 degrees is exactly half that, so that's 0.5. So the sine of 30 degrees is 0.5. Hurts. Okay. So from the table you can go and, from the equations, and you can go on and figure out what those are. And it's pretty straightforward, what I've already illustrated to you. All right. Now here is a thing we'll use periodically, not all that frequently, but it's a nice thing to know, especially if you're doing proofs, which I tend to try to avoid as much as possible. There's some people who are math majors. Are either of you math majors? Okay. They need to know the proofs probably better than what I teach. So this is called the triangle inequality. And if you think about it at all carefully, you see it makes obvious sense. Remember, if you're adding two vectors v and w, the component, the resultant vector is going to be, say, somewhere here. Okay? Now, if you added the magnitude of v to the magnitude of w, that's really going to exceed that. Because the only way that would be the same is if v was this direction and w was that direction, then you add them together and they're equal to each other. If you have v in one direction and w in some other direction, the magnitudes cannot possibly be as great as the sum of these two vectors. Cannot. And that's what the triangle inequality tells you. For any two vectors, v and w, the magnitude of the sum of those two vectors is less than or equal to the sum of the magnitudes. Okay? There are some things that look like they sort of make sense, like this, the sum of two vectors is the like when we're doing linearity and place types of things, you know, there are certain things that are true. This, though, with vectors, is a triangle inequality. It's not inequality, except in one particular thing. Equality holds only if v is equal to w and w. I'm sorry. If v is the zero vector and w is the zero vector, or w is the zero vector, either one of those, or if w is a multiple of v, any multiple of v, well, any positive multiple of v, then that works. Then that you have a strict equality. Like I said, if they were on the same line. Okay, and these are some of the illustrations that show that. Okay. Let's take u and v and w, such that they both have some positive quantity. To say is v plus w, they're not collinear, so v plus w is going to be some vector out in that direction. Okay? Well, if you took the magnitude of v, which would be about that, and then the magnitude of w and put it here, that's going to be less than that. We're only doing magnitudes then. The magnitude of v plus w is less than the magnitude of v plus the magnitude of w. Same thing here. That's the magnitude of v, about like that, and the magnitude of w, much longer. Magnitude of the sum is less than the magnitude of the sum of the magnitudes. Okay? And this one, here's your v and there's your w, The magnitude of V itself is longer than the sum of those two. Okay? So surely every case you consider like this is going to be less than or equal. Actually, I hadn't noticed this. These look like they're perpendicular to each other. So we know now that the magnitude of V plus W is the square root of this magnitude squared plus the square root of that magnitude squared. And that's going to be greater than just the sum of those two factors. Got it. Okay. That ends 12.1. Sorry. My morning class was in chapter 5. This is. Are we out of time? I'm sorry. We'll start next time at 12:2. That was a much longer section than I was. Well, I had to take that break in the middle. So we'll start next time at 12:2. Again, I'm not assigning any homework here, but any of those homework exercises you want to do to make sure you're understanding this, fine. You're not going to be tested on this. Let me get something in place here. Remember, we're just going to do quick run-through. I'm going to try to be quicker than I was today. 12:2 is shorter, and 12:3 is fairly short, dot products, and 12:4 is the cross products. Okay, it's a little bit longer. And then points in three or planes in three space, we'll hit that. It's pretty short. Okay, and 12:6 is then where we actually begin Cal 3, survey of quadratic surfaces. So I'll try to pick up the speed a little bit. Just wanted you to get the basics of vectors down, since I couldn't remember a vector. Have you had physics already? Oh, you have. Okay, so you already knew it, but you're just in physics now for the first time. So you'll run into this again, and the next one should go a lot faster. Sorry about today, and I'm sorry that my head was wacko today. Now I'm losing my voice as well, so I don't know. I only got 5 minutes between the next classes. Are you in the next one? Yeah, but you're not. You're tomorrow. Okay. What are we doing here? I don't know what I hit, but it was the wrong thing, I guess. Let me